So what is the idea here? We all have been talking about VLC, and it has a major drawback, and that it consumes a lot of energy. So when you turn on your light for communication, roughly 85% of that energy goes for illumination, 15% for communication. What does that mean? That means that if you're in a dark room and you turn on your light because you need to see, and on top of that you add a little bit of energy to communicate, it's a good deal. But if you come to a room where there's enough ambient light and you turn on that LED only for communication, not because you see you need light, it's a pretty bad deal, because this can consume more than Wi-Fi. Okay? And why is energy important? Because I'm not sure if you know, but by 2013, so that was 7 years ago, we humans were using 50% more energy moving bytes than moving all airplanes around the world. Right? That's a lot of energy. And roughly between 1/3 and 1/4 of that is related to wireless communication. So we really want to find ways to reduce. Light gives us bandwidth, that's awesome, but at the cost of energy. So what are people doing? Of course, you cannot turn the sun on and off. If you could turn the sun on and off at very high speeds, you would have a broadcast channel for the Earth. But people are trying to find ways to modulate that. As it was mentioned by Borja, and a little bit by Domenico, one of the ways in which people are modulating light intensity from ambient light is with these LCD displays. And it works in a very basic manner. It's basically like fast blinds, right? So you send a 0, then the light goes by, you put a very small voltage, and then the light is blocked. And then you put, again, the voltage to 0, and you can communicate information. What does that mean is if you see this LCD here, you will see that it becomes transparent and non-transparent, transparent and opaque. So you will see a little image on the back that starts appearing and disappearing, appears, disappears, appears, and disappears. And that's the way in which people are using ambient light for modulation. Now, let me see the time. What is the issue? It's very slow. So there are some of these materials, well, actually, there are some other materials that are very fast, but the ones that are being used right now in the community are very slow. So to go from transparent to opaque state, it takes a few milliseconds. The same thing if you want to go down. So what happens is that this axis is the frequency, how fast we start modulating that LCD. And this is the difference that we have in contrast between the maximum transparent and opaque state. So if you start modulating your signal very slow, you got something like that. You start modulating a little bit faster, 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 and then you don't have any contrast. And this is what we are showing here. And so what is the problem? It's because we don't want to cause flickering. We cannot use these frequencies that are below 200 hertz. And because the signal to noise ratio will be too low, we cannot use that part right there. So we are only constrained to using a very part of the narrow band that we have there. This is, I think, related to what Domenico was explaining, which is the basics for ambient light communication, and is backscattering with light. So in this application, you will have this car. Oh, the idea is that a car is moving around, and then it will say, I am a car. And then this signpost will send information back saying you're in a 60-kilometer region. So how do they want it to work? Is here you just have a normal LED light. This is supposed to be an LED and a photodiode. So in this direction, I'm sending information at a very high data rate, hundreds of kilobits per second, megabits per second. So this is very high. On that side, you see this little thing here? It's supposed to be that LCD shutter that allows light to pass through or not, and a retroreflector, right? So if you have a mirror and you have a light source here, this is how the light beam goes. If you have a retroreflector, the light goes back to the source. So in this case, you start modulating this at a very low speed, and you start reflecting back the information, but this is very slow, less than 1 kbps. Okay? So you may wonder if you want to use this for ambient light communication, what if we just put sort of this device, this receiver here, you put a photodiode somewhere, sunlight will come back, will come and hit this, and you will be sending it back to the sun. Not very useful. You could say sunlight will come, I will diffuse it and transmit it towards my photodiode. But then this method has a problem, which is that it causes a lot of flickering. These pulse shape methods that Pupula was talking about, what happens is that if you send a signal and you see the power spectral density, sometimes you don't see it going under 200 hertz, so no flickering. But when you start sending some specific patterns, this starts spreading out, causing flickering effects, right? And that's something that we really would not like to see. There's how to overcome that. Let me see time. There was this very nice piece of work in which they could use any light source, or even sunlight, and then they put a small tag here, and that tag is something basically like these two components. I will explain that in a moment, and this removed. So what they do is sunlight comes in this way, and they play a trick in which out here you have colors sort of changing, color shift keying. Now, the person that is right here will not see any change in the colors, nothing at all. But the camera with a polarizer will be able to see those changes. And because when you change polarization, usually flickering is not that strong, they are able to get, let's say, ambient light information here, zeros and ones on the other side. But they transmit only 14 bits per second, so it's not that much. One of the things that we have been doing in our group is to try to have this sunlight, the emitter. We have this little box that is roughly this big. These are these LCD shutter. So light comes this way. It's diffused in different directions. Here, this little box has sensors and a keyboard extension, so you can plug and then just send any message that you want. And then what we do is we transmit information via FSK to a receiver. Well, you cannot see it so well here, but it's a box roughly this big that has an e-ink display. Here it has just a simple photodiode, a solar panel. And then we can start decoding that information. And the good news is that because it's frequency shift keying, we are always above these 200 hertz that cause flickering. And on top of that, because FSK was designed by default to cope with changes in amplitude, it's also very robust. Because if you have pulse shapes, you have a cloud passing by or any changes, that can affect the signal quite a lot. But if you have just FSK, we really don't care much about it, as long as we can still detect some frequency. So here I would just like to make a little bit of a pitch about why this area could be important. So if you divide roughly wireless communication for humanity for the last 100 years, if you see active radio, this means a radio that you need to put energy on to send information. So this has been going on for the last century. Then people realized that we were running out of bandwidth. Around 2000, really started working really hard on visible light communication, but you need a light that you can transmit information. 5 years ago or so, there was this concept of ambient backscattering using radio waves that are already in the air, and then you just start reflecting them back and forth. So you use existing radio waves from cellular towers, from TV, and then you just start backscattering them. And then now, people are trying to look into light and passive. And why is that good? This part gives us bandwidth. This is low energy, because you use tons of energy when you need to excite an antenna or you need to excite an LED. Okay? Any questions for that part? Yes?
What is the maximum range that you achieve with the LCD shutter?
1 kilobit per second.
Not the range and the
Oh,
distance.
60 meters. We have been able to achieve 60 meters, 70 meters in the Netherlands, which is very cloudy. So I guess in Spain you will be able to achieve a much better range. But at that range, we only achieve close to 180 bits per second. So, right, so if you increase the range, you don't get the same data rate.
The sunlight that is coming, that is getting into the receiver, it doesn't affect too much?
The sunlight?
As an interference?
Oh, yeah, no, because if you think about it, so our receiver is inside this little box. So it's the same as if you are blinded by sun. If I just do this, then I can see very well, right? So it's kind of, yeah.
So that's 60 meter. What was the data rate that you used for?
80 bits per second. But I think it could be done, so we are using devices that cost only, how much? 3 euros, guys? 4 euros? There are some devices that cost 5,000 euros, 4,000 euros, and then you would be able to transmit much more. So you go from milliseconds to microseconds. So there's some other data, but it's expensive. Let me just wrap it up with a couple of concepts. So LED to photodiode and camera. Sunlight, you can do it to photodiode or camera. This is what Pixel did, the color shift keying. But there's also now a lot of work that is going into screen communication to camera communication. Okay, so if you are watching TV and you have your Google glasses, you can start getting a lot of information coming your way. And how are people doing that? The basic idea is the following. So let's say that you have a movie coming to you at 60 frames per second, right? So that's usually what happens. Then I will be sending images at 150, 120 frames per second. So I will double it. But when I double it, let's say that your image, the original one, at 60 frames per second, was using the colors in this part in the middle. Actually, you don't see it very clearly, but this is divided into 3 zones. Right? Zone 1, 2, and 3. 2 is the original color of the video that you wanted to watch. But if I double the rate, then let's say, and I'm transmitting green, I put a green that is a little bit darker, a green that is a little bit lighter. I submit those 2 frames, you subtract one from each other, and at the end you get something like a QR code. So from your perspective, you are actually watching a movie and nothing is happening, but from the camera perspective, you're transmitting information. And this can give you around 100 kilobits per second, right? But it's almost like a MIMO system. And the last thing that I have to show you guys is, question, sorry? Somebody? No. And the last thing that I wanted to show you is using light a little bit more for sensing. So this is actually something that we did with Tridonics, right? And the idea was the following. So Tridonics has these lights, and it has some color sensors on the light. And they wanted to track people, but not with cameras, to invade privacy. They say, let's just use, can we use just these color sensors? And this is the idea that we had. So imagine somebody's walking. This is a color sensor. So basically a single pixel camera. It combines all the colors within the field of view into a single color. And as somebody starts walking by, we are able to create an optical signature. So this is, let's say, time. And then the optical sensor will start mixing the color of the floor, your shoes, you continue walking, your skin, your pants, your t-shirt, and all that. And then I create a unique optical signature. So the next time that you pass, if that optical signature exists, I can say, oh, I have seen that person. I don't know who that person is, but I know that that person has been moving around. Roughly, what you will see now is there are 2 sensors, one here, one there, and then somebody's passing by. Well, it's blue and blue jeans. So it's a blue sweater and blue jeans passing through the 2 sensors. Later, you will see another person that will be passing by, which is a little bit more of like a dark, sort of greenish with still the blue jeans. Okay? So they are passing through the 2 sensors. And here what you will start seeing is that sensor 1 will start detecting this optical signature. And then you just apply some machine learning techniques, and then you will be able to track that person moving around. Of course, that person takes off the sweater, pop, we think it's a different person. So to wrap up, I would like to consider you guys visible light, not only, of course, between the LED and the photodiode. There are multiple ways to achieve that, and it's not only about communication, but also about sensing. With that, I would like to conclude not only this talk, but the tutorial as well, And I would like to say thank you for spending all this day with us. Okay? Thanks, guys.